Hello and welcome to 6. I'm Noah Walberger, and this is my attempt at introducing pure mathematical thinking to a very wide audience with minimal prerequisites. So this is going to be a course in pure mathematics, which is going to investigate an interesting area that we can access in a very elementary way. The audience is going to be motivated high school students and beyond. Any lay people who are interested in learning about pure mathematics from the ground up. The only prerequisites, really, at least to begin with, are going to be arithmetic with natural numbers. Roughly what you would have learned from primary school education. So very minimal prerequisites. Okay, and the aim of the course is to illustrate what pure mathematics research is really like, to give you a direct and tangible experience of this. And we're going to develop concentration skills, logical reasoning, careful organization, and hopefully a love of mathematics. Now, usually, in order to access pure mathematics, which is a rather esoteric and usually thought of as difficult subject, you require many years of undergraduate education followed by graduate school. We're circumventing all of that, and we're doing it in a way that doesn't really connect with any other thing. So we're just going to investigate some independent, very elementary situation, and we're going to explore this really interesting landscape around it, and perhaps we're going to meet all kinds of interesting things. So our aim is actually not to get to any particular point. Okay, I'm just going to be explaining a branch of pure mathematics which is all about the number 6. So it's mathematical content which you're really not going to find anywhere else. But ultimately, we will be, I can promise you, touching base with really classical and lovely 19th century mathematics that actually engaged the interest of a lot of really prominent mathematicians. So there will be something at the end of it that's going to be really fascinating. But that's not our aim. Our aim is just to explore. So I hope you're going to join me for this. I hope you'll take a notebook or maybe your laptop or iPad, whatever, and follow along and listen carefully to everything that I do and try to understand everything that I say. And even if you're not used to enjoying mathematics, I hope you'll get a sense of what the subject is really about. Careful definitions, clear notation, and an organized approach to analyzing patterns and making connections. So we are going to start by taking 6 objects. And we're going to consider these objects to be the numbers 1, 2, 3, 4, 5, and 6. So the entire course is going to be built up from these 6 initial objects. We will generally write them in black. So whenever you see numbers from 1 to 6 in black, you should think of them as being our initial objects. And we're going to be thinking about having containers for these 6. So we have a container of 1s, a container of 2s, and so on. And we're able to take numbers from these containers and combine them to create more complicated objects. Okay? So that's the initial thrust, is we're going to be creating objects from these 6 numbers. And we are then going to look at the patterns that we can form from these. Now, I want to stress that the actual arithmetic associated with these 6 numbers is going to be irrelevant. So we're not going to be adding or multiplying or doing any kind of arithmetic with these objects. You can think about these as just sort of short forms for the names of 6 things. So I could have used pens or coins or any number of things, but it's convenient to use these things because they're all very familiar and because there's a natural order to them which will be useful to us later on. So what our aim is at first is to create expressions just involving grouping or arranging these kinds of objects in various ways. And when we group these basic objects together, we have some choices. Whether we're going to create patterns or groupings which are ordered or unordered. And another choice that we can make is whether repetitions are going to be allowed or not allowed. So this is a very important kind of distinction, and this is going to provide sort of a theoretical framework for us moving forward. We have to talk about how to organize data or information in various ways, ordered or unordered, repetitions allowed or not allowed. So let's talk about the very important idea of organizing mathematical objects. In mathematics, there are generally 4 different ways of organizing data or other objects. I like to call this the LOMS framework. And there are 4 kinds of objects: lists, ordered sets, multisets, and sets. And let's talk about what these things are and the notation for them. Notation is going to play a very important role in this course. So we have to understand precisely what it is that we're writing down and what the meaning of the things that we're writing down. So the first one, a list. A list is an ordered collection where repetitions are allowed. So it's ordered, means there's a first, there's a second, etc. And repetitions are allowed. So here, for example, is a list. It's, first of all, enclosed in these square brackets. The entries are 4, and then 3, and then 3, and then 5. And they are ordered by the presence of these commas that separate subsequent elements. So first there's 4, then there's a comma, then there's 3, then there's a comma, then there's 3, then there's another comma, there's 5. And we can see that repetitions are allowed because there are 2 3s. Notice that the objects that we're actually using are all from our fundamental 6 allowed objects. That's going to be happening throughout the course. The actual ingredients to everything are just one of these 6 starting numbers, okay? Now, the next data structure is an ordered set, or short, Oset. I should probably underline that too because that's important. Okay, an Oset. So what is an ordered set? It is a collection which is ordered, but now no repetitions are allowed. No duplication. And the notation for that is these curved brackets. It's sometimes called braces. Okay, that kind of brace. And there's commas to indicate that things are still ordered. So this is the ordered set 6, 1, 2. Our next data structure is a multiset, or for short, Mset. It is unordered, but repetitions are allowed. It's unordered, so there are no commas. That's the way we represent an unordered collection. There are no commas that put the elements in their proper place, that separate them and kind of lock them in. You can think about the contents here like the contents of a box. The elements are allowed to move around and the object itself is not changing. The brackets are the square brackets, the same kind of brackets that we have in a list, and that tells us that repetitions are allowed. Okay, so the brackets tell us whether repetition is allowed or not, and the commas or spaces tell us whether the thing is ordered or not. So multisets are unordered and repetitions are allowed. And the final one, which is actually in modern mathematics by far the most familiar and widely used, is the set, which is unordered and repetitions are not allowed. And our notation for a set is going to be consistent with what we've said up here. The fact that it's unordered means that there's no commas separating the elements, just spaces. And the fact that no repetitions are allowed is the same as for an Oset. These are these brace brackets. So we can look at these four kinds of data structures and we can tell just from the form whether we're talking about a list, an ordered set, an Mset, or a set. Now in classical mathematics, sets are dominant. But for us, that's not going to be the case. We are going to maintain flexibility and in fact a kind of a feeling of equality between these four different ways of organizing things. That's going to be very important. So it's crucial that you spend some time staring at this and get yourself used to the notation that we're going to be using. Now in my Math Foundation series, I talk quite extensively about these data structures, and in my algebraic calculus course we actually use them, so you may have had some experience with that if you've watched some of my other videos. And if you want a little bit more information, you can go to the Math Foundations series and find out more about these. But this is really all you really need to know, is what these four types of ways of organizing mathematical objects are and how the notation tells us which one is in front of us at any given time. So just to reinforce that, let me put all that information in a little array with four boxes, and over here we have the ordered objects and the unordered objects in this first row and then in this second row. So the list and the ordered set are ordered, the multiset or Mset and the set are unordered. And over here in the columns represent whether repetitions are allowed. Here they're allowed, and over here they're not allowed. So there's a list, there's an example of a list. It's ordered and repetitions are allowed. Here's an Oset, there's an example of it. It's ordered because of the commas, and it's repetitions not being allowed in this case, as you can see by the type of brackets. Over here is an Mset or a multiset. It's unordered and repetitions are allowed. Unordered because the spaces between them replace the commas. So spaces means that you can move things around. It's unordered. And these brackets tell us that repetitions are okay, just like in the list. And finally, the set has these braces telling us that repetitions are not allowed, but it's unordered, as we can see by the spaces between elements instead of commas. So for example, with this set, you could change the position of the 6 and the 4, and it would be the same set. With the ordered set, you're not allowed to change the positions of, say, the 2 and the 3. That would be a different ordered set. Over here, you're allowed to change the 1 and the 2. You could move that 1 there and move the 2 over there. That would be the same Mset. So one more important aspect of these things is a measure of how many elements there are in them. Okay, so this thing here has 5 elements. 1, 2, 3, 4, 5. We're counting. This one has 4 elements. This one has 3 elements. This one has 4 elements. We can make that part of the name, okay, by adding the number of elements in front of the data structure. So for example, here's another example of a list. The list 2, 4, 4. This is a 3 list. It's a 3 list because it has 3 elements. Here's an ordered set or an Oset. It's a 2 Oset. We write it like this, a 2 Oset, because it has 2 elements. Here is a 5 Mset. It's an Mset with 5 elements. And here is a 4 set. It's a set with 4 elements. So let me emphasize that this notation, this setup, is very logical, okay? But it's different from what often is done, because classically the emphasis is on sets, and usually we don't write sets this way. We write them in classical mathematics with commas. So we are separating our usage here from the classical one. You have to remember that, okay? So when we write something like this, you have to recognize this as a set. When we introduce commas, that means we're introducing an ordering. Does that make sense? I hope it's sort of logical. Okay, it is logical, and it's sort of consistent, but it's something that you have to remember. All right, so let's use these data structures to create some new objects out of our 6 initial objects. First, let's give our initial objects a name. Okay, we are going to call them, these primary objects, 1, 2, 3, 4, 5, 6, we're going to call them nodes. Have a look, nodes. Right, so this is a node. That's a node. So this is just a terminology that we're introducing. We're going to agree that node, where it might have some other prior meaning in ordinary life, for us, node is going to refer to one of these 6 objects. And to emphasize the fact that this is very specific usage of this terminology, I'm going to introduce what I call German notation. I'm going to capitalize the first letter of this word. That's going to immediately remind us that this is a fundamental kind of object. Now, what is this 6 that's floating beyond here? This 6 is in blue. It's not a black 6, so it's not the same as this 6 here. This 6 is telling us how many nodes there are. Okay? We have a very simple world here, so one of the things that we're going to be doing at least is counting things when we create them. Okay? So there are 6 nodes. Okay, now it's time to introduce some new objects. And the first thing that we're going to introduce are the edges. The new objects are going to be called edges, and what they are 2 sets of nodes. 2 sets of nodes. What does that mean? It means it's a set with 2 elements. So it looks like this has this brace kind of brackets, and there's no commas separating the elements. And there's going to be 2 elements, and these elements have to be themselves nodes. In other words, they have to be amongst our basic nodes. And we're going to introduce some abbreviated notation, because we're in this happy situation where we're always only going to be using these 6 numbers. And that means we can save ourselves quite a little bit of work by being judicious about our notation. It's going to be very important for us. Okay. So instead of writing set A, B, I'm just going to write A followed by B. So in this world, the world of this course, A, B does not mean the product of A and B. It means the 2 set whose elements are A and B. But with a further proviso that we're going to arrange things so that A is less than B. Right? A and B are both elements in here. They're amongst these nodes. And while the set is unchanged if we permute the elements, we are going to write it so that the smaller entry, or the smaller node, comes first. Okay, so what effectively do these edges look like? Well, the simplest edge is 1, 2. Okay, 1, 2, that's our short form for the 2 set whose elements are 1 and 2. And then there's 1, 3. That's the next kind of logical one. And then there's 1, 4, and then there's 1, 5, and then 1, 6, and then 2, 3, 2, 4, 2, 5, 2, 6, 3, 4, 3, 5, 3, 6, 4, 5, 4, 6, 5, 6. Notice that I've listed them in a somewhat logical order, starting with the simpler or the smaller first element in this representation. So I'm using the natural ordering on the 6 elements to list these 15 edges in a reasonably sort of consistent pattern. And there are 15 of them because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 such edges. So this is, I hope you see, what we're kind of doing is we're taking planet Earth, okay, with all the complexity and human interactions and all kinds of things, and we're taking a rocket ship and we're leaving planet Earth far behind. We're not aiming towards applications, okay? We're now on this distant planet and there's nothing there except for these sort of 6 nodes. Actually, we have these containers of 6 nodes, so we have lots of the nodes. And we're just going to create stuff, okay? And that is going to be our pure mathematical exercise. Very abstract, very unconnected with applications. Okay, we're just wanting to explore what we can actually say about 6 things. And this is a good place to start with our 6 nodes and our 15 edges. Okay, so we're going to now want to introduce one more type of new objects, and then we'll be in a nice position to finish this first lecture, and I'll give you some homework. Okay, so the 15 edges that we've just written down, if you stare at them, you might realize that any 2 of them have a possible connection. So we're going to introduce a definition. We'll say that 2 edges are incident precisely when they share an element. After all, an edge is actually a 2 set. So if we have 2 edges, we have 2 sets, and we can ask, do these 2 sets actually contain a common element or a common node? So for example, the edge 1, 2 and the edge 2, 5 are incident because they share the node 2, while the edges 3, 6 and 1, 4 are not incident because they don't share any common nodes. And now we're going to introduce new objects, a little bit bigger and better than edges, which are called meets. Okay, what's a meet? Well, a meet is a 2 set of non-incident edges. So you may have to slow down and really get your head around this, but it's possible to understand it completely. I want you to understand it completely what we're doing. So this is a 2 set. Okay, so it's a set with 2 things inside it. And those 2 things are each edges that we've just defined. But the 2 of them have to have this property that they are non-incident. In other words, the nodes that appear are not overlapping. So for example, here is an example of a meet. It's a 2 set with, well, an edge there and an edge there. And these 2 edges we've just seen are not incident. So this is a viable meet. Now we're going to save ourselves a little bit of time by introducing more streamlined notation. We're going to exploit again the fact that we can write our edges rather compactly. So we can write this 2 set compactly by putting the edges together with a little period or dot between them. But we're going to do it in such a way that the first element of the first edge is less than the first element of the second edge. So maybe I might say that, okay, here, where by convention we're going to agree that the 1 here is actually less than 3 in the order of the nodes. We're going to do that so that we have a canonical way of describing this object, because we could rewrite this 2 set by interchanging these 2 elements, okay? But by agreeing that the first element of the first edge here is going to be less than in the ordering of the first element in the second edge, we guarantee that there's always a canonical way of writing a given meet. And now I claim that there are exactly 45 meets. And now we come to your first homework. So homework number 1 is to list all 45 meets. Same kind of way that I listed the 15 edges. I want you to list all the 45 meets. And hopefully in an organized way, in a systematic way. in a way that makes it easy for somebody to check that you've got all of them, and in which there's a pattern, hopefully, that it's pretty clear sort of how to keep going. So if this homework is too onerous, then probably this course is not for you. But if you can say, yes, this is not so bad, I'm going to organize my thoughts, I'm going to understand what these words mean, and I'm going to write out all 45 of these meets, and I'm going to do it, and I'm going to check that it's correct. Then you have an orientation towards thinking carefully, thinking logically, thinking in an organized way. And those aspects are sort of at the heart of doing pure mathematics. So to summarize what we've done today, we've introduced, using a prior discussion of data structures, crucially introducing lists, ordered sets, multisets, and sets. We've defined, first of all, our fundamental nodes, and then 15 edges, and then 45 meets. So we already have now the start of a small landscape, all built up from our 6 nodes. So there's going to be lots of interesting things happening. I hope you're going to be joining me for the rest of this course. I'm Nolan Wildberger. Thanks for listening.